everyone. Welcome and thank you for joining tonight. And welcome to our next hackathon session. And today we have a very exciting topic. It's Helidon and Loom. And I like to welcome Peter or Petr Nagy from the Oracle team. Hi, Petr.
Hi. Yeah, the correct pronunciation is Peter.
Okay, cool. Hey, thank you for being with us tonight, and we are very excited to have you and about your topic Helidon and Loom.
Yes, so basically I've been with Oracle something like 11 years. I started as a sales consultant. I was responsible for WebLogic, coherence, and stuff like that, and I then moved to the product development team, which is still responsible for. I mean, the area is the same. I'm still responsible for WebLogic, coherence, and now for Helidon as well.
Ah, coherence, interesting. Yeah, cool.
Basically, we call it, enterprise cloud native Java tools at this moment.
Ah, okay. There were some changes about coherence, right? In the last
Yes,
last year.
exactly. Yeah.
It's open source now.
Yes, correct. Okay, here we go. So yeah, since we are Oracle, I always need to include this safe harbor statement, even if I'm talking about open source projects. So okay, so basically, what is Project Loom? So basically, what I will talk tomorrow, what I'm going to talk about tomorrow is basically how we integrated as an experimental feature project Loom with Helidon. I think most of you already know what is Project Loom, but if not, so there's a very easy single sentence which can explain what is it. So something like to introduce an easy to use high throughput concurrency and new programming models on the Java platform. I think the most important word is the new programming models, because I think in the last years you heard a lot about reactive and asynchronous programming. So if you want to achieve some better scalability, better performance, then you might hit this word, the reactive and asynchronous programming, and the journey then just start on that way. So you need to use a different approach. I mean, comparing to the traditional synchronous word in the Java programming language. Okay, and so this is one of the main reasons to introduce Project Loom. I'm not going to talk really in details about Project Loom and what is about the status, the limitation, and stuff like that. But I will show you that the current release of the early access release of Project Loom, which is integrated in JDK 17, how it is integrated with Helidon, and what can you get if you test from performance perspective. Okay, so just a quick introduction about threads. So because Loom is introducing a new approach of thread management. Back to my previous slides. So as you may heard virtual threads, but how we call it in Project Loom, these are not virtual threads. Basically, these are user mode threads. Okay, so not operating system level threads, but user mode threads. Okay, so a couple of words about threads. So why we introduced threads a long time ago. So some of you, I think, don't remember those times when we have a single core in a server, even in a server computer server machine. So in that time, it was a solution to introduce for processing threads, which called lightweight processes. We can call it lightweight processes. And you can start more lightweight processes within the process. So it's called thread, and it allows you multitasking in a concurrency way. Okay, so how to run multiple tasks at the same time within the same process. And it is important that within the same process, because you might want to share the resources between the threads. So for example, memory and open files and stuff like that. What is important here, the thread is supported by the operating system. So as I mentioned, those time typically the CPUs has a single core, so we wanted to utilize better that single core. So this is why we introduced the thread. So basically, again, about the multitasking and the concurrency. And how it was introduced, as I mentioned, so it is supported by the operating system level. What does it mean? So operating system threads must support all use cases and all programming language. So which means a very low optimization. So the result of this, that the thread is a quite heavy resource. Okay, so it requires almost 1 megabyte stack size. So whenever we want to switch context between threads, it requires such amount of memory, and also it requires expensive resources from the CPU to switch between the threads. Okay, and because of these constraints, there are a limited number of threads, typically on a regular hardware. Okay, so we can't really tell an exact number, but it's typically less than 1,000. You can test it, so you can scale out. You can create a thread with a dummy program, and you can test on a certain hardware or a certain operating system. Threads was introduced in Java from the beginning, basically, but as we know at this moment, it was introduced in Java 1.2. And basically that java.lang.thread wraps a native operating system thread. So whenever you create a new thread within the Java process, you will use a native operating system thread. Okay, I think most of you haven't heard about that. In that time, especially at the beginning, Java 1.1, there was also a kind of thread management was introduced. It's called green threads. Okay, so that was also a kind of approach how to manage better the resources. I mean the CPU resources, the core, and it is more or less close to the, I wouldn't say close, but that was a similar approach like Project Loom at this moment. Okay. However, in that time, the implementation was very bad, and especially when that time new CPU appeared with more cores, the JVM, the Java process couldn't handle in the right way the multiple cores. So the green threads approach wasn't the best idea at this moment. So it was eliminated from the Java 1.3 version. Okay, so what about the problem basically when we are using threads? So typically we using threads to complete multiple tasks in a multitasking way, as I mentioned. The problem is around when we use threads, lightweight processes, we can call it in this way. So the problem with this, when we have some slow backend. So if you do some application development, you typically think about the slow database response, okay, a big query or stuff like that. When you need to wait really a long time, so for example, 1 sec or more, even more, to the result, which means that during that time, that thread will be blocked, okay? What you can do to continue your work with your application, you can open another thread and do the task using that thread. Okay, so this is the typical approach, I mean the traditional approach in case of Java. So let's do a really short math here. So for example, we have 500 requests per sec, and unfortunately every request has some slow backend. I mean, contains some slow backend invocation, which takes 2 seconds. Okay, so if we have 500 requests per sec, and all the requests needs to complete, need to execute, need to call a slow backend, which takes more than 2 sec, that means we need 1,000 threads on average at a given point. Okay, which means at least just to maintain that thread, I mean that amount of threads, we need 1,000 megabyte memory, just for the stack data. Okay, and this is just to manage that amount of threads. Okay, so this is very very resource intensive, and also again, don't forget from CPU perspective, it is also very expensive the switching between the operating system level threads. Okay, so that requires a lot of CPU resources. as I mentioned at the beginning, it was really notable that it required a lot of time to switch between the threads. Over time, we had multiple cores in one CPU, multiple threads, stuff like that, and the CPU got faster. So we may think, okay, over time we are okay with this approach. However, when we nowadays moving to the cloud, it's again a very, very important factor how much resource we consume, because we need to pay for that. Okay, and usually we pay for memory usage, we usually pay for CPU usage. Okay, so again, we also started to count every CPU cycle. So it's not just about that we are operating like company Netflix and we need reactive or asynchronous approach or really sophisticated thread management because we have a huge amount of performance issues. This is again another approach when we are moving our load, every small load into the cloud, then every CPU time will matter when we need to pay for that. Okay. Okay, how we can solve it? So a lot of solution happened in the past for that. So obviously there were some operating system level solution, what we couldn't control basically. And there were a couple of operating system independent non-blocking solutions like within the Java platform. So for example, the non-blocking IO, the Java non-blocking IO. And also, as I mentioned, nowadays what you can heard in many conferences, there are a lot of topic around. So we started to use the reactive and asynchronous approach. Okay. Obviously, the first approach using this, the first use case to use this approach, as I mentioned, basically happened that those companies where were really huge performance requirements and scalability requirements, okay? Because as I mentioned, so the operating system supported native threads were limited. It requires a lot of resources. The context switching requires CPU resources. So it's not just about, giving a bigger hardware or paying more in the cloud, but also keep the pace with the demand, okay, the load demand. Okay, so basically what reactive and asynchronous approach? So there are a couple of ways how to implement this. So for example, one of them is the event loop, or you can use the stream approach. So basically what we are doing right now, we are trying not blocking any thread for any moment. And it's a different approach how we manage the execution of the task using, for example, one single thread. Okay, what we do here is we try to manage, this thread execution, the pool and stuff like that within the application, okay, using third-party libraries, okay. Obviously, Java added a lot of feature here. So for example, the future, the callback and stuff like that, async await. So we have a lot of features from the JDK, from the Java itself to do this. However, it is still introduce complexity, a different approach compared to a synchronous world, what we have done before in a simple Java application development. So what's the problem with this basically? So the problem is that it's pretty hard to go to change from the synchronous word to asynchronous word. So if you have started to develop something in an asynchronous way, you need to really, you had to go through a couple of phases when you really understood that word. And also another problem that you can't just start to use an asynchronous approach within existing synchronous application, because that can break many things there, or it will not be a pure asynchronous solution, which means at the end of the day, it will have a performance penalty. Okay, so these are the problems. And also there are other problems with this. So for example, if you think about, if you use the asynchronous approach and you need to debug that code, or you need to maintain that code, that also has more complexity compared to the traditional synchronous approach. However, when you can change, when you can do your application development in this way using with third-party libraries, right, like Java or stuff like that. So there are a number of third-party libraries out there which can support in different way to this approach. Then you will have a really performant application. Okay, but this can be a pretty long journey in some cases. So what you need to decide, whether you will stick to the synchronous approach, less scalable, much maintainable, you don't need to break your existing application, you don't need to rewrite the whole application, or you will go with the asynchronous way, which means typically you need to rewrite your existing application if you want to introduce. It's much more easier if you just write a new application. Obviously, there you can easily introduce this approach. And also you need to have a better understanding for that programming model. So this is why Project Loom has started, basically, because they realized the necessity of this asynchronous approach. I mean, the better thread management, much more lightweight thread management. So this was the reason why they started to work on this. And the result is Project Loom, basically. So a couple of things there. So there is a fiber, what we can call the user mode thread, basically there. It is made, it consists two things, the continuation and the scheduler, okay? The continuation is basically the task itself, which will be completed by the thread, the executor thread, and the scheduler is responsible to schedule these tasks. Okay. Currently, the scheduler is implemented using the well-known for-join framework, which was introduced, as far as I remember, in Java, maybe 7. So currently, that is the scheduler in the Project Loom implementation. However, it can be other, and that is work right now, the scheduler. Okay, what is much more interesting here? So when we have the thread management, I mean this kind of thread management, which is not exactly the same. So you can't map the operating system level thread to this thread. Okay, obviously. So for example, there are certain limitations at this point, at this implementation. So for example, in certain cases, you can't call, for example, native API from using fiber. What you can do with the native threads, okay, yeah, the java.lang.thread. But on the other hand, the context switching is much more lightweight, I would say. There is no such kind of thing of context switching. So we are resuming and stopping the fibers. Okay, so this is a bit different, but thanks to this, it requires much less resources. Okay, and what is also important here, it is very, very lightweight, so it doesn't have really have a huge footprint. So you can have almost whatever you want, millions. Okay, obviously you will not use such amount of, especially if you think the current asynchronous approach, you can use much more efficiently, much less threads, basically. But theoretically, you can have thousands, millions of virtual threads. Okay, so again, important thing is here, this is managed by the Java virtual machine, so it is nothing has to do with the native the operating system thread. However, basically the continuation itself is completed using an operating system level thread. Okay. Okay, the goal was to use the existing API. So this is what I would like to demonstrate, how easy it was to introduce into Helidon. So we have an asynchronous executor service within Helidon framework, and how easy it was to replace to use to Project Loom, to the virtual threads. Okay, and what gives Project Loom, as I mentioned, so somehow we can go back to the old well-known world, and we could write synchronous code, which will be executed behind the scenes thanks to the Project Loom in an asynchronous way. Okay, as I mentioned, there are a couple of temporary limitations. Some of them will be permanent as well. Currently, the latest early access release available in JDK 17. I'm going to use this version, and you can have further information on the link here. Okay, a couple of words about Project Helidon. Not sure how many of you heard about Project Helidon, maybe in this series or any other place. So I'm going to just give a real short overview for those who are not familiar with Project Helidon. For those who already know what is Project Helidon, that is just 5 minutes or 10 minutes. So grab a coffee or something like that and come back. Okay, so Helidon architecture. Helidon is based on NetE, okay, which is a very powerful and fast network protocol framework. And on top of that, we have the Helidon SC API, which is an asynchronous non-blocking API, functional style API. And on top of that, we have implemented the microprofile specification, and we call this API Helidon MP. So using that API, you can use the microprofile specification. So you will get exactly the microprofile annotated driven development style, which is similar to the Java EE, Jakarta EE development style. The extensions covers what we integrated already, or what you can integrate using the CDI extensions, because CDI is the key component of the microprofile specification. And on top of that, you have your application, the microservices application itself, okay? We have a command line interface to create project and, for example, to run your application in a mode. If you modify any code during the development, it will rebuild the changes, and you will see immediately the changes in your application. Just really a short sample how it looks like whenever you use the Helidon SC API. As I mentioned, it's a kind of functional reactive style of API. So both codes do the same. So it is a REST endpoint, a hello REST endpoint, which will give a hello world string. On the right hand, you can see the Helidon MP API, as I mentioned. So this is similar to the Java EE, Jakarta EE API specification. So you can have the annotated driven easy development. Okay, this is just a slide about how Helidon, microprofile, and Jakarta EE relates to each other. If you're familiar that microprofile has started with a couple of Jakarta EE specifications. So namely, it was the JAX series, the JSON, the JSON parsing and processing and binding, and as I mentioned, the CDI, which is the key feature of microprofile, because every feature is available using the CDI integration. Okay, and there you can see our Helidon implementation. So we have implemented the microprofile specification with a lot of features which allows you to easily create a microservices application. So everything what you need to create a microservices application, so configuration, metrics, health check, fault tolerance, messaging, security, everything what is really necessary to build your microservices application. Okay, Beside these, we also added a couple of features. So, for example, database client, web client, what are reactive asynchronous client for database access, for calling REST services, and also we added more security features and the gRPC also, as well as a modern high-performance communication form within a microservices architecture. Okay. What I would like to also highlight in case of Helidon, that we do support the Graabium native image, which is important because I think you may have heard a lot about native image. It's a very exciting tool nowadays. So what Oracle Lab did with Graabium, so they have write a completely new just-in-time compiler using Java. And since this is a brand new compiler, it has a mode that not just optimizing the code during the runtime, so how the Java works. So usually you compile the source to the bytecode, and during the JVM execution, bytecode execution, the JVM start to optimize the code and compile certain parts of the bytecode to a native executable code using the JIT compiler. And the result is that if you have such compiled and optimized natively executable code, it will be much faster. Okay. And the idea behind the native image, okay, why we just compile certain part of the code, I mean the hotspot of the code, why don't we compile the whole Java application into a natively executable binary? And we can do this. However, it can have a lot of limitation depending on the framework what you use, depending on the libraries what you use, because you can imagine when the native image compiles the Java code into a native executable binary, it needs to reach, for example, all the parts of the code. So, for example, if the code contains some reflection API, which is not reachable during the compilation time, because some dynamic class loading method invocation happens during the runtime, that is unknown during the compilation time. So we can solve this situation if we support the native image compilation. So for example, the framework itself, the library itself, what you are using in your application, if that supports the native image compilation with certain helper classes, with certain configuration, then you can compile your application, the whole application. Okay, otherwise it can fail in the compilation. Okay, but Helidon supports native image, so you can, in most of the cases, if you don't use such third-party libraries which doesn't support or can't be compiled using the native image, then you can compile your microservice application into a native executable binary. Why is it important? Because you will get a pretty amazing numbers regarding the resource requirements and also with the startup time, for example. So there you can see a couple of comparisons here. So in this case, there you can see the traditional JVM approach. So we have a jar file, what we are going to execute. And on the right block, you can see the native image numbers. So what I did, it's a simple hello world application, which has a REST endpoint, a JSON response. And I did measure the application size itself. In this case, the jar size itself. In this case, the native image size, which is bigger. However, it doesn't require the JVM. So don't forget, whenever you have just a 6 megabyte jar file, in case of Helidon SE, it still needs the Java runtime environment, which can, consume even 100 megabytes if you package into a Docker container. Okay, but in case of native image, you just need this size of application. Okay, so you don't need to package any other Java runtime environment, so that is not required. Startup time. This is also a very, so even in case of Java, which requires the full JVM start, to serve the first request, it's under basically 1 sec. Okay, but in case of native image, when we don't have JVM uptime, okay, so immediately we can serve almost immediately. So there you can find the numbers. Okay. Oh, sorry, this is the serving. Sorry, the first line is the serving first request. The second one is just the startup time. Okay, so the startup time under 1 sec, but serving the first request is not is almost 1 sec as well. And in case of native image, it's 47 milliseconds, so it's lightning fast. So it's ideal for serverless solution or, for example, scaling such application. Okay, so it's even to initiate a container in Kubernetes takes longer than just start the application within the container. Okay, and also the memory footprint, again, because that memory also contains the Java runtime environment requirements. Okay. Further information, what you can find about Helidon, there are a couple of things here. So now get back to our topic, how we integrated Loom into Helidon. So what we have done so far, this is really amazing. We had to only change 3 files, and 2 of them are source codes, and 1 of them is just a POM file, an example. Let me show it how it looks like. So it's it's very, very interesting. So let me open this pull request. So if you see here the changes, Helidon is an open source project, so you can see everything on the GitHub. So there you can see we had on JAX executor service, okay, for Netty. So this is what we had so far. And when we wanted to introduce the Project Loom, we just monitor one configuration. You will see this configuration whenever I will run our application in virtual thread mode. So this is the property what I need to pass. And in this case, we are initiate an executor which is part of Project Loom. So Project Loom provides for us this kind of virtual thread executor, and immediately we can use this thread executor instead of our current JAX executor service, and that's all. So, and we are done. So basically, it works right now. Okay. Let me show you how you can use basically the Project Loom in your average Java application. This was, I think, yes. So there are 2 ways how you can use Project Loom in your application. So basically the thread API. Traditionally, if you want to manage the thread on your own, then you can start, in this case, a virtual thread. Start virtual thread. So this is what you need to use in case of Project Loom. And what we are using here, the executor service, and as I mentioned, we are initiating this one, the new virtual thread executor, okay, using that code block. And immediately we got that executor service, and we can use that executor service to complete our tasks within Helidon. So this is why I'm showing this, because again, so Project Loom goals is to compatible with the current API. Okay, so it's really easy to introduce Project Loom in many applications. Okay, certainly there can be limitation which can break this easy integration, but for us the experimental integration was such easy. Okay, so let's go back to the presentation. Okay, so these are the code changes and how you can test, basically how you can run your application using Project Loom. So again, there is no LTS release with Project Loom, so there is only an early access build, which is currently with version 17. So you need to go here and you need to download this separate build, and then you can use Project Loom. Okay. You can see the disclaimer here. So this is not for production, and functionality is subject to change, but you can start to work with that in an experimental mode. Okay, how it looks like, my test application, you will see immediately. So it's a very, very basic dummy application, which basically, it has two REST endpoint. One of them is a sleep, where we can give a parameter, and in this case, our thread will sleep for that amount of millisecond. Okay, so this is just somehow emulate that this thread is blocked for a certain amount of time because it needs to interact with a slow backend. Okay, and there is another one which called info. This is another REST endpoint where we can get the thread name. Okay. Oops. Okay, so for the test scenario, I use for the tools, I use Vegeta for the load test. I need to do some warm-up. It's useful, especially we are talking about Java. And what I would do, I will emulate an 90 millisecond delay in my thread, a block in my thread, and I'm going to perform a stress test with 1000 requests per sec for 10 sec. Okay, I'm going to open the JConsole just to examine the amount of number of threads and how it will work during the load and stuff like that. We will have 3 scenarios. So whenever you use, for example, Helidon or any other frameworks, it has a default thread pool size, basically. Helidon calculates the default thread pool size based on the machine. I mean, what kind of CPU the machine does have. In my case, it's a 4-core CPU, so it will have 8 threads in the pool initially. Okay. The second scenario will be the virtual threads, so using the Project Loom itself. And the third one is that I'm going to tune our initial thread pool size to 100 native threads, and let's see what we'll get with that amount of thread pools, the threads in the thread pool. Okay, so let's do the test. Okay, so what I have so far, it's basically a basic application. Okay, so what I did is just generated a quick start microprofile project using Helidon. So if you go to the helidon.io, you find a quick guide under the microprofile API. You will get immediately a Maven command how to generate this quick start project, and I just added that source code what I showed in the presentation. Here you can see. So there's a sleep service. This is what are by default generated with the quick start project. So you will have the sleep service. I mean, this is the sleep service. These sources will be available under my GitHub repository when the video will be available on the MicroStream webpage. So as I mentioned, it is just a very simple REST endpoint which will just block the thread in a certain amount of time. So what we will give, which will be 90 millisecond at this moment. Okay, so let's go back here. So this is the sources, very simple code. Okay, I have downloaded the JDK which contains the Project Loom. Okay, I have the load tool. It's called Vegeta, and that's all. So we can start it. Okay, so first I'm going to start my application, which was already built. So let me. So yes, I have my Helidon Loom mp.char application. So I'm going to start this in a pretty regular way. I haven't added this JDK to my path, so I need to use in this way. So, Okay, here's my application. Okay, it has started. And okay, let's do some warm up at the beginning. Okay, so I'm going to run the this one. Yep, this way. I need to write into this. Oh, sorry, this one. This will read the result. I mean, this will print the result. Okay, I need to call. Okay, so I'm going to call this endpoint using the tool. We are going to use 2 cores, and the duration is 10 sec. As I mentioned, 1,000 requests per sec, and the result will be written to this file. Okay, so let's do some warm up at the beginning. Okay, in the meantime, let me open my JConsole. I think this was here, yes. Okay, let me connect to my application. Okay, so what we can see here, let's go back for a moment. Can you see my terminal? Okay, I hope so. Okay, so what you can see here, okay, we are on after the warm-up. So as I mentioned, initially we start with 8 threads in the thread pool, and after the warm-up, we had more. Okay, don't ask why it has the same name, but we have 18 at this moment, okay, which were responsible to complete the request. Okay, so this was the size of the thread pool. Okay, this is the basic Helidon executor approach. Okay, so at the end of the run, we ended with 18 threads in the thread pool. Okay, so let's do a test right now. Okay, so let's see the result. So it will run 10 sec. Okay, and okay, we are done, and let's print the result. Okay, I think this one, yes. There you can see. So most of the calls, the response time was under 100 millisec, okay? So almost 90%, okay? But almost 10% was above 2 sec, okay? So this was the result of the load. In case of the, I would say, the traditional approach, which is still based on a very sophisticated thread management. Okay, so let's see what will happen if I start with the Project Loom. Let me move away my zoom. Okay, oh, it will not be. Okay, there is it. So let me start using VirtualThread. As I mentioned, I need to pass just one property, so which is virtual threads. So there you can see. So I'm using the JDK 70 with Project Loom, and this is the property one I need to pass to activate the Loom thread management. Okay, and I'm using the same jar. Okay, so let's start it. Okay, it is running right now. So let's do first some warm up. Okay, let's write that virtual thread. Oh, I forgot to connect at this moment, but it will not be a problem because we are working with virtual threads. So let me join to this version. And once we have joined to this JVM, there you can see the threads. Maybe I did something wrong. No, we are good. So now what we have here we have this thread pool as well with 8 threads. But what you can see here, the for join pool scheduler, which has currently 4 threads, and this was enough to complete the requests. Okay, so this is what we have so far, and let's see after the warm-up what we have. So run again. So if we are going back here, so it's still under 40 threads, which includes all the necessary threads. Okay, so not just completing the response. Okay, so let's see the result for this one. And this will be the virtual threads. Yep. So, oh, that's interesting. Let me do this one run again. I expected a bit better result. However, I think we are still better because we don't have any response above 400 or 500 millisec. Okay, just few of them. Okay, so let's see again the result. Yeah, this is kind of. So what we have so far is most of the response time is below 300 millisec. Okay, and yeah, the most of under 200 millisec. Okay, I not really understand because I think it's something with Zoom, because whenever I ran without, I mean, previously it was much better, and I can hear my fan at this moment in the computer, so maybe something is happening with my computer. Okay, but this is still good. Okay, so we got better performance. Let me run it again. Just I'm really curious about this one. Maybe I can, yeah, and it's dropped below. Let me disconnect this one, but it shouldn't be too much effect on this. Okay, very curious about why I didn't get much more clear result. Okay, so one last try. Yeah, it's getting better, but still my fan is really loud, so it means something is happening. So this is what I would somehow expected, or better, what I got usually. Okay, so usually what I got is most of the calls under 100 millisec, but this is also basically under 200 millisec. So this is better, but not enough better, but better. Okay, so finally let's check what will happen if I will give 100 thread to my thread pool using the traditional approach. Okay, so nothing else. Okay, so yep, so this one where I can define the core pool size. Basically, this is a minimum pool size. This will be 100 and the maximum as well. So I'm going to work with 100 thread, which is a operating system native thread. Okay, so let's start the application in this way. And immediately I can start the console itself. Oops. This one. Okay, so yes, there you can see we have 100 threads. So let's see how it will complete this load test. Okay, so that will be 100. This will be the warm-up. So I'm going to run again this one. Frankly speaking, it was far better without, I don't know, I can think about Zoom. because, yeah, let's see what we'll get with this scenario. Okay, so let's, okay. So there you can see, even if we have 100 threads, which should be not a problem for this computer, we got worst results comparing to the virtual thread approach, where we had only 4 threads which was allocated, which were allocated to complete our tasks during the load test. Okay, so even if we have 100 threads, the 4 threads using Project Loom is outperformed. Okay, and also compared to the initial one, which was pretty good. However, oh no, this one, sorry. Yeah, however, 10% was more than 2 seconds. Okay, so there was a peak at most likely at the beginning, which was lower than the average. And yes, if I go back here, maybe I can show. Yeah, so this is what I wanted to. This is what I expected basically. So this was what happened previously 1 hour earlier when I have tested the environment before the presentation. So this is what I expected. I don't know why I got this result, but what you can see here, still there is some load even if I'm not running the load test, and I still can hear my fan, so something happens. What I think is just the zoom as an overhead. Yeah, so basically this is what we have so far. Yep. Let me run once again, but I don't expect, so there you can see, if you can see my activity monitor, something is going in the background, and I can only think about Zoom because nothing else. I have switched off, closed everything else. So this should be, it's interesting. It's interesting. So let me run once again the virtual thread mode, and let's see whether I can get a better result or not. Yep, this was the virtual thread mode, and let's see. Yep, is it running? Yes. I'm very curious about this one, but I don't expect better result. As I told you, something is running in the background, which is interesting experience, but because it means that it may affect more the JVM level thread management compared to the native thread management, operating system level native thread management. Okay, let's do the run after the warm up, and let's see the result. Okay, and yeah, that's interesting. I still can't get. Okay, maybe I should show this this demo on live presentation without any Zoom. Okay, let's go back to the presentation. But basically, this is what I have in this topic. So the conclusion, basically, I wouldn't say at this moment that clearly wins, but wins this test case. So still, I can say that the virtual thread management was far better because we had only 4 threads which could complete the whole load test. And I think if we go into the details, we still get better response times on average, and for the whole picture compared to the native thread management. However, the native wasn't so bad. So we were under, you know, most of them were under a couple of 100 millisec. So it's not bad. But what is interesting here, what I maybe have show. Also, the virtual threads are cheap, so I forget to show that the memory consumption is also lower in case of the virtual thread, because that doesn't require much more thread from JVM perspective, comparing if we have an initial 100 thread in the pool, or if we have only an initial 8 thread, but it will go up at the end of the load test, something like 20 or more thread. And again, so we can write synchronous code and we can use as usual, and we got the almost the same effect comparing if we need to write asynchronous code, which is much more complex and can have problems with certain dependencies, third-party libraries, and in most of the cases not easy to introduce in our existing application. However, it's also a good question, because when we are talking about legacy or existing application, we need to consider the fact that whenever Project Loom will be available in the JDK, the official JDK, we still need to upgrade that application to that level to use the virtual thread benefits. Okay, so we need to deal with this as well. Again, I don't know the exact date where you can expect the Project Loom in an official JDK, so not a separated, not a separate build, which is an early access build. I don't have any information about the exact date, but we are getting closer. So this is the reason why we integrated with Helidon. So you could, or we can start to work with Project Loom, and we can see what we can do, what are the limitations, and how we can write your application using this feature. Yeah, I have a couple of questions here. Okay, so last year some parts of Coherence code was not available as open source. Is the entire code of Coherence now available? It's a good question. As far as I know, yes. Yes, it is available, but I definitely need to check if any other part is missing from here. No, it should be available, the whole Coherence. As soon as Loom is released, will reactive programming become obsolete? It's a good question, a very good question. You know, I think if some companies, some developer put a lot of effort into such approach, I think they will not change immediately, because that, you know, that is an existing running application. You don't want to break that running application in production and stuff like that. But I can imagine if it will work in a way how we promote, so how easy it was integrating with Project Helidon. There you can see maybe it's also easy to integrate with your application, with your future applications. So what does it mean? You don't need to care about any more synchronous approach or reactive frameworks or stuff like that. Okay, so I wouldn't say obsolete, especially at the beginning, but later I can tell you, frankly speaking, I don't like the reactive approach. Maybe the reason that I'm not a daily basis developer. So if I would do reactive programming on daily basis, then probably I would be okay with that. However, since I touch the code to write tutorials, workshops, example application, I still didn't get the, you know, the whole picture, and sometimes I need to stop to think about, okay, how should I write this to really make it work, and when I need to debug, so it's complex. So I'm pretty sure most of the people will choose this one because it's much more simpler. Okay, when fiber is part, how does scheduler know result of IO is ready to resume the fiber? Must use async and call back behind the scenes, right? So it means instead of developer write async code. Okay, frankly speaking, I don't know the answer to this. So what I did so far, I have just worked on this integration, so I didn't really went into the details how it happens behind the scenes. So unfortunately I would rather recommend to find the proper Project Loom description. Sorry for that. Okay, Ken Helidon SC has annotation as well. No, there is no such plan at this moment. So we wanted to keep Helidon SC as a minimal API to write a really fast and efficient application. Okay, so if you need every millisecond, so if you need every byte in your disk, in your memory, you can use Helidon SC API to write, a functional style reactive application. Okay, if you want to use annotation, use microprofile. Okay, so in case of Helidon, for a moment. Does it use proxies and reflections? In case of Helidon IP, yes, but in case of Helidon SC, there is no process annotation, or there is no any annotation. Why are you using reflection to get executor for VirtualThreads? It's, okay, that's a good question. I don't know why we choose this way, but I don't have clear answer at this moment. So I didn't implement it exactly this integration. So I need to check what was the reason why we use this reflection. I'm pretty sure it's around the approach what we use under the CDI server, and also to support somehow the native image compilation. So I think this is the reason, but I'm not sure, 100% sure. What I would recommend, go to our Slack channel, Helidon Slack channel, where our engineers can answer to your question, or Stack Overflow. So we continuously monitor those channels as well. So you can ask there this question, and we will answer that. I think we are done. So thank you for your attention. I hope you find it useful. And if you have any question, as I mentioned, use Stack Overflow with Helidon tag, or our Slack channel, public Slack channel, and you will get answer almost immediately there.
Yeah, great topic. And thank you for your time, and it was great to have you. Okay, thank you everybody for joining again. Bye-bye.